Okay, hi again, everyone. So I would like to tell you a little bit more about the application of graph states in various quantum technologies. So this is a continuation of the graph state tutorial that we started. So the applications that I would like to consider are three. So the first one is measurement-based quantum computation, which is the most well-known application of graph states. The second one is on quantum sensing. The third one is on quantum repeaters. So let's start with the measurement-based quantum computation. And what I want to do first is I want to give you the central idea behind measurement-based quantum computation. So the central idea is something called gate teleportation. So the way it works is that let's say you have two qubits. So the first qubit is prepared in some arbitrary state, and the second qubit is prepared in the plus state. And you want to make some change in the state psi. What you could do, so you want to do some certain rotation, let's say. So what you could do is you could entangle those qubits first by using, let's say, a CZ gate. So that will give you the state, right? So now it's an entangled two-qubit state. And then what you could do is you can measure. So you can measure one of the qubits, but you can do measurements in arbitrary along arbitrary axes. You don't have to measure along the z direction, for instance. So here you make a measurement on the first qubit in, let's say, this basis. So this basis, as you can see, you have a degree of freedom phi to choose. So it's some basis that you pick. And what turns out to be the case is that if you make a measurement of this form, then you collapse the state of the second qubit into one of the following two states, right? And these states look almost the same as the initial state, except that the 0 and the 1 are now a plus and a minus. And also there's an additional phase, a relative phase between those two amplitudes of alpha and beta. So you have the e to the I phi there that hasn't been there before. And that was introduced by your choice of the measurement basis. So in some sense, this is the basic idea behind measurement-based quantum computation, is that you can introduce some changes in the state that you're working with by entangling your qubits and making measurements on them. So in general, so this process, or at least this operation on the state of the qubit, could be thought of as starting with the initial state, applying some unitary rotation along the z direction with some angle phi that introduces the relative phase between the 0 and the 1 of your state, and then doing a Hadamard, because now the 0 and the 1 are plus and minus, as you saw. And then, depending on the measurement outcome, there's an additional Pauli X that you may or may not have to contend with. But generally speaking, you can keep track of these additional Pauli phases, or the Paulis that come at the end, and you can correct for them at the end of your calculation. So you could also do that. You don't have to necessarily worry about these Paulis that come up at the end. The relevant part here is that there's a rotation along the z-axis that's happening with some angle phi that's leading to a relative phase difference between the 0 and the 1 of your state. So that's the relevant thing to think about in this example. Now, this could be general. So you don't just have to do a rotation around the z-axis. You can do an arbitrary rotation. For that, you need more qubits. So let's consider that. So let's say, again, similar scenario, you have an input state, and you want to do some arbitrary rotation on that input state. So what you could do is that you can have, for instance, 3 other qubits, all prepared in the plus state, and then you entangle all the qubits using CZ gates between them, right? So you have 3 CZ gates here, one between these two, one between these two, and one between these two. And that's why you have these links, similar to a graph state, right? And the goal is, just by using single qubit measurements, can we make some arbitrary rotation on our state psi, right? So that's the goal. And what we have to keep in mind is that if we can perform Pauli X and Pauli Z rotations, or rotations along the Z and the X direction in the following way. So if you have first a rotation around the Z-axis and then another around the X and then another around the Z, then you have effectively made an arbitrary rotation. And that just follows from an Euler decomposition of some arbitrary rotation. You can always write it in this form as a sequence of rotations around the Z and the X axes. So that's the goal. Can we have some rotation on, or an arbitrary rotation of this form acting on our state psi? If we can, just by using single qubit measurements, and if we can, then it turns out we can, in fact, do arbitrary, single qubit gates, which is part of having a quantum computer. So to do that, the measurement basis that we have to choose is along the xy plane, and the angle by which, and the angle from the x-axis would be given by phi. So for each qubit, that angle would be different. And so we have to do 3 qubit measurements. So 3 single qubit measurements, basically. One with an angle phi1, one with angle phi2, one with angle phi3. And again, those are measured with respect to the x-axis in the xy plane, right? So if you do those qubit measurements, what you'll end up with is that your 4th qubit, so the one that is left that you haven't measured, will end up in this following state. Now, let's look into what's happening into this qubit specifically. So as there's some Z rotation that's happening with some angle phi1, then there's an X rotation happening with some angle phi2 that also depends on the measurement outcome of, with the sign that depends on the measurement outcome at the first stage. And then another rotation along the Z direction, the measure with some angle phi3 and with a sign that's determined by the measurement outcome in the second stage. And then there are some bunch of single qubit operations that are also happening, right? So the way to interpret this is that you would first notice that up to corrections based on the measurement outcome, you have an arbitrary rotation here in the first 3 steps. First 3 steps is just a Pauli, is just an Euler decomposition of an arbitrary rotation. Give or take this additional plus or minus that you will have based on the measurement outcome. So that's exactly what we wanted to do on our state. We wanted to do an arbitrary rotation, and that's what we did. And the additional single qubit Paulis that we have here at the end, those come based on the measurement outcome, right? And those we can correct for at the end by applying the corresponding single qubit Paulis, right? So, or Pauli measurements. So up to that correction in terms of the measurement based on the measurement outcomes, we have performed an arbitrary single qubit rotation on our state psi. So this is the general idea behind doing behind the measurement-based quantum computation. Now these are just single qubit gates. How about 2 qubit gates? You of course need 2 qubit gates for universal quantum computation, and 2 qubit gates are done in a similar way. So again, let's say here you have an entangled state of multiple qubits, and then you do measurements in certain bases, and then the state of the remaining 2 qubits become entangled based on a given gate. So you can kind of generalize this idea to 2 qubit gates also, the one that you saw for single qubits. Right. So what are the differences between this measurement-based quantum computation and the regular circuit model for quantum computation that people are more familiar with? So generally speaking, with the circuit model, you start with your qubits all in the product state, and then you do single and 2 qubit unitaries to entangle these qubits, and then you measure at the end, and hopefully you end up with the right measurement outcome, or right computational result, basically, for your desired computation. So in the cluster state model, you don't start from a product state. In fact, you start from this entangled state of qubits. Generally speaking, it's a graph state of this form. It's a two-dimensional graph state that has this lattice shape. And then what you do is just you do single qubit measurements and classical feed forwarding. So notice there are no two-qubit measurements anymore, or sorry, two-qubit gates anymore, right? So this makes things easier, at least in theory. Of course, it's quite difficult to prepare these entangled states, but once you can do that, all you have to do afterward is single qubit measurements and feed forwarding, and no need to do any two-qubit unitary gates. And then at the end, you measure the qubits that you have, and you also will end up with some outcome for your quantum computation. So as you can see, the difference is that in the circuit model, the entanglement happens during the computation, whereas in the whereas in the measurement-based quantum computation model, the entanglement happens before any computation is done, and then the computation is made by just doing single qubit measurements and feed forward. So there are some things to keep in mind. So the first thing is, it's true you may need a big graph state to start with, but you can generate that part by part. You don't need to generate the whole thing all at once. And that's because you're not consuming that state all at once. You are consuming that state in portions, specifically the ones that you're measuring. So you can create it in sequence. So that makes things easier, typically. And also what you need to do is that you need your measurements to be quite fast in comparison to how coherent your system is, your photonic system. And also in terms of the feed forwarding, you have to be able to implement them fast enough. So these are some considerations to keep in mind while trying to implement graph states for quantum computation. And in terms of the physical systems, so photons are typically considered the most standard qubits for measurement-based quantum computation. So the idea is that you can start by entangling those photons and create a graph state offline. You don't have to do this during the computation, so I can prepare that in advance and then do your computation afterwards. And with photons, single qubit measurements on arbitrary basis is quite easy to do. And feed forwarding is also quite realistic with photonic systems. Of course, there are other physical systems that are appropriate for these measurement-based quantum computations. The cold atoms, for instance, are another example. Here you can have an Ising-type interaction between your atoms, so it makes them quite natural for measurement-based quantum computation. And also, you can generate these types of states in a single time step. So that's also quite a useful property for these systems that you can use to your advantage, basically, when generating these graph states. Good. So that's the first part of the applications for graph states in terms of the experimental highlights. So here you can see some examples of implementing these types of measurement-based quantum computation. So now let us move to quantum sensing. So how do graph states apply in quantum sensing? So as a reminder, the problem was that there's some parameter of interest, let's say a delay phase, phi, that we're interested in. We want to measure this quantity, right? So let's say we have some material and we're sending light through it and it's accumulating some delay phase, and we want to know what that delay phase is. So what we do in quantum sensing is that we prepare, let's say, our photons in some initial state, we send it through the material, we let it accumulate the phase that's unknown, and then whatever photons come out, we measure them. And then based on the measurement outcome, we make a guess of what that phase would be. So regular quantum parameter estimation tells us there's a limit to how well we can estimate this value phi. And turns out that estimate depends on how much Fisher information we can have about this parameter. So the estimate turns out to be bounded from below, but by 1 over the Fisher information. So the larger the Fisher information, the less uncertainty we have in our estimate. Here, delta phi squared is the uncertainty or the variance, right? So it turns out that for independent qubits, for instance, if you prepare your photons separately without entangling them before sending them through this material, then the Fisher information scales in as the number of the photons, so scales as a function of n linearly, which means you can have larger and larger Fisher information the more photons you use, but that only scales in a linear way. As opposed to, let's say, when you have an entangled state, such as a G8C state or a G8Z state, the Fisher information turns out to scale as n squared. So it scales much better in comparison to when you don't have an entangled state at the input, right? So this makes G8C states naturally more suited for quantum sensing in comparison to regular non-entangled states. Now, how about graph states? So G8C states are not exactly graph states, they're locally equivalent, but how about other graph states? So how close can we get to this limit, this fundamental limit in quantum sensing? So to answer that question, we have to think about the graph in terms of the vertices, and each vertex has their own neighbor. So let's say we have a qubit I, which represents one of the vertices. And let's say it has neighbors, which we denote them by n of I, right? So if qubit I and another qubit j in our graph have the same neighbor, then we say that n of I is equal to n of j. So that's just a way of saying they share the identical neighbors. And the way it looks on a graph is exactly like this. So as you can see here, qubit I and qubit j share two neighbors, right? So they're connected to this qubit on the top, and this qubit in the middle, right? So they have the same neighbors. Now, why am I saying this? Why am I mentioning this? Because it turns out you can divide the qubits in your graph in terms of their neighbors that they share. And this is an interesting way of thinking about your graph. So for instance, what I want to show you here is an example where your qubits are colored based on their neighbors. So whether they share the same neighbor or not, rather. So here, the blue qubits are the ones that you saw above. They're qubits I and j, right? They're the same color because they share the same neighbor, right? So they both share these two qubits. Similarly, those two light blue qubits have the same color because they share the same qubit, namely this one in the center and each other. And because of that, they have the same color. Now, the remaining qubits, this one, doesn't share the same neighbors with anybody else. So it has its own color, and the one in the center doesn't share the same neighbors as anybody else. All the same neighbors. So that's why it's in a different or a separate color. So that's kind of like the division that we're thinking of our qubits in a graph, right? So if we can divide our graph or think of our graph as subsets of qubits that are classified based on the neighbors that they share, then turns out that the Fisher information is just equal to the sum of the square of the number of qubits that belong to the same, that have the same neighbor. So I will give you an example of how that is computed. So here's an example. So take this linear graph state, for instance. So here, nobody shares the exact same neighbors with anybody else. So this one, for instance, the first one only has one neighbor, this guy. And this guy, the second qubit, shares, it has the same neighbor as it is also neighboring this first qubit, but also has another neighbor. So they don't share the exact same neighbors. And the same for every other qubit. No two qubits on this chain have the same neighbors. So because of that, you have 6 different types of qubits, each with their own neighbor, right? So then the formula for your Fisher information is just given by, so you saw the previous slide, it was just this formula, right? Where the subsets here, each subset of qubits with the same neighbors just includes one member, right? There are no 2 qubits that have the same neighbor. So there are no 2 qubits in each of those subsets. There's only one qubit. So we have each of the values of these subsets is equal to 1, and then we have 1 squared, right? And we add them for a number of times, equal to the number of subsets. In this case, we have 6 different subsets because nobody shares the same neighbors. So we add that 6 times, and that gives us 6. So the Fisher information here is pretty low. And the reason why I'm saying it's low, it's because we can compare it to other types of states where this could be much higher. So here's an example. So think about the state that you saw earlier. So here we said that there are a few qubits that share the same neighbor, namely these two, this dark blue ones, share the same neighbors. And the light blue ones also share the same neighbors. So because of that, we have lesser number of subsets that our qubits belong in. So these two, for instance, belong to the same subsets because they share the same neighbors, and so are these two. So therefore, what we have, if we start from the top, we have a subset with only this qubit, so that's 1 squared plus subset with this qubit and this qubit, so that's 2. There are 2 qubits, so there are 2 squared plus one that only contains one subset that only contains this qubit, so plus 1 squared, and then plus a subset that contains both these 2 qubits. So that's plus 2, so plus 2 squared, and that's equal to 10. So 10 is a much better Fisher information than 6. So what that means is that this graph state is better for quantum sensing than this graph state, because the Fisher information that this graph state conveys is much larger than this graph state. Now, if you think back about the G8C state, we said that the Fisher information scales as n squared. So if we just take n squared, n here being the number of qubits, so that's 6. So 6 squared is 36. So we have a lot more to go. So far we start with 6 for our Fisher information, and then we said that this graph is 10. But we can go all the way to 36. So are there any graph states that are better for quantum sensing? So they get us closer, let's say, to 36 compared to the 2 that we saw right here. So the answer is yes. And it depends, as we saw, on the number of qubits that have the same neighbors. So here's a very good choice. So think about the graph that you just saw, and now let's modify that graph such that most of the qubits have the same neighbor. So here, if you look into the graph on the right, so this graph has those blue qubits, all of them sharing the same neighbor, the one in the center, and the one in the center doesn't share the same neighbor with anybody else. So here you only have 2 types of qubits. So there are 2 subsets as opposed to 6, for instance, that you saw earlier. So these are called star graphs, and these are quite advantageous. And if we want to compute the Fisher information for these types of graphs, then we only have 2 terms. The first term is the one for this subset, the blue qubits, the ones that share the same neighbor. So that's 5 qubits, so that's 6 minus 1 squared, that's their contribution into the Fisher information. And then plus the one remaining qubit in the middle, so that's a subset of qubit 1. There's no other qubit that shares the same neighbors. That's plus 1 squared. So we'll end up with 26, which is closer to 36 than what we had before. Because this graph had only 10 in terms of the Fisher information. And this has 26. Right. So we can do even better than this. So star-type graph states are already quite good in terms of the Fisher information they provide because of how most of the qubits in that graph has the same neighbors. But here, you can have even a better state, which is a fully connected graph states. Namely, these are the graph states where each qubit is connected to each other qubit. And these types of graph states you can actually prepare quite well. If you start from graph states, let's say this one has 6 qubits, you start from a star type graph state of 7 qubits, and then you measure the center in the y-axis. And then that's how you end up with this type of a graph state. So it's not that difficult to prepare. Now, if you have this type of a state, every single qubit has the same neighbors, shares the same neighbors. So there's only one subset, one type of qubit. So the number of subsets here is equal to 1, right? And the number of qubits in that subset is equal to 6. So we just plug that into the Fisher information formula. And we end up with 6 squared, which is 36. So that's exactly equal to the G8C state Fisher information. So this is the best we can do with our graph states, is if we had this fully connected graph, then we can maximize the Fisher information, and thereby we can also minimize the uncertainty in the sensing of our noise parameter. Right. So that's what I want to say about quantum sensing. Finally, let's talk about quantum repeaters and how graph states apply for quantum repeaters. So the idea, just broadly speaking, is that let's say you have Alice and Bob, that they're interested in having an entanglement between them for certain applications, let's say quantum key distribution. And they are generally unable to just do that by sending entangled pairs between them, because that distance could be very large, like hundreds of kilometers, and you're likely to lose your photons in that case. So what you do instead is you create repeaters. So Alice and Bob are on either side of this line, and what you do is instead of sending entangled pairs from Alice all the way to Bob, you send it to intermediary nodes in the center, and then by doing that, you use more of your entangled pairs, but you have a higher likelihood of establishing a connection through what I'm going to describe next, which is entanglement swapping. So what's the idea here? So the idea is as follows. So let's say Alice is on the left and Bob is on the right. So Alice sends an entangled pair to an intermediary node in the center, and so does Bob, right? And the intermediary node in the center makes a Bell measurement. And with a Bell measurement, depending on the measurement outcome, Alice and Bob will end up with having an entanglement between themselves. And this is what's called an entanglement swapping. So an original entanglement that used to be between Alice and the intermediate person and the intermediate person and Bob was swapped to become an entanglement between Alice and Bob. Now, this is a probabilistic event. So turns out there's a 50% probability that this will succeed, but there's a 50% probability that it will fail, in which case there is no entanglement between Alice and Bob. And because of that, we have to think about entangled states that are a bit more complicated than simple Bell pairs. So the entangled states that are useful for quantum repeaters turn out to be of this very specific form. So this specific form has two unique features. The first one is that it has a core of qubits that are fully entangled with each other. And the second feature is that each qubit from the core has an arm. So an arm extends out, and there's only one qubit connected in that arm, right? So these are the two features of these repeater type graph states. And these states turn out to be quite useful for establishing a connection between Alice and Bob, as opposed to just Bell states. So how we would do that? So what we would do is, let's say Alice is on the left side and Bob is on the right side. What you will do is that you will send half of the states to Alice and the other half, so you split this graph in half. So the first half goes to Alice or to the node closest to Alice, and the second half goes to Bob or the node closest to Bob. Right? So just to show you how that looks like, So think of Alice as being on the left and Bob being on the right. So you prepare these repeater type graph states here in those state preparation nodes, right? So these blue regions, and then you send them. So you send this one, half of it. So you see that it's cut in half. The first half is sent to the left, the other half is sent to the right. Similarly for the other node, half of it is sent to the left and the other half to the right. So what do you do next? So here is an intermediary node that two halves of our repeater state arrives at. And now we do a Bell measurement, similar to what we did with our Bell states. Right, so now each arm, so we have three arms. So each arm is subject to a Bell measurement. So a Bell measurement here, and a Bell measurement here, right? And let's see what happens. So let's say that this Bell measurement succeeded. And on that repeat, on the one on the left, the repeater on the left, or the node on the left, this measurement succeeded. And the node on the right, let's say this measurement succeeded, right? So there's some form of success of those Bell measurements that happened, for instance. So how would you establish a connection between Alice and Bob depending on these measurement outcomes? So first of all, you will measure the remaining qubits, the Pauli Z, that will take them out of the graph state. So we've discussed this in the previous part of the presentation. So you'll end up with no qubits. Over here, those are taken out on those red regions where we measure the Pauli Z. And for the blue parts, to make a full connection between Alice and Bob, or a direct connection rather, you just have to measure these qubits in the X spaces. You have to just measure the Pauli X of those qubits. And that will connect the Alice all the way on the left to Bob, which is all the way to the right. Right? So this is the idea behind using those repeater type graph states for quantum, for establishing a quantum connection or a quantum network between Alice and Bob, right? Another thing to keep in mind, besides the fact that these types of graph states are useful, is that we can also encode the photons that are representing this graph state. And the reason we want to encode them is that we want to protect them from loss once we send them through optical fibers, let's say from Alice to an intermediary node, or let's say from Bob to an intermediary node, right? So we can encode the qubits to protect them from loss. So that makes this graph a little bit more complicated. So the qubits that we encode, let's say the ones in the center, or the ones in the core, these blue ones. So we have to think about each of them as being encoded in a tree-like fashion. So that's useful, turns out to be useful for preventing loss from happening. Or once loss happens of one of the qubits, then you can still recover the information encoded on the qubit through error correction. So that's the idea. So we have to think about these qubits as encoded logical qubits rather than just physical qubits. So that will make our graph a little bit more complicated. So if we just plug this little graph in each of our qubits here, this will give us the type of a graph that we need for a repeater. So it will look like this, right? So you basically have a graph, a repeater type graph with a tree-like encoding for those core qubits, right? And overall, the graph will look like this. So this is a very loss-tolerant repeater graph state because it's made such that any photon loss will be corrected for by error correction mechanisms. So this makes this specific graph state very useful for quantum repeaters. Okay, with that said, this is kind of an overall broad summary of what graph states do, what are graph states, and what are the applications. So we mainly talked about motivation behind graph states, why we use them, and how they apply to measurement-based quantum computation, how it applies to quantum sensing, and also quantum repeaters. And also, finally, I want to thank John for motivating me to make this presentation. I also want to thank Sophia for giving me a lot of her slides that I can work with. Okay, so with that said, thank you very much for listening.